Okay, so welcome back again to another video. In this video, we're going to talk about the reduction of aldehydes, ketones, and carboxylic acids, and we are going to reduce these compounds using lithium aluminum hydrides. Okay, so the reaction is like this. Okay, let me first write the reactions, and then we can go into the mechanism. So first, let's talk about an aldehyde. So let's take an aldehyde like this: CH3CH2 C double OH. Here you have an aldehyde. Now if you add lithium aluminum hydride and water, okay, the water is essential, right? When you write an answer in your paper, you need to add water in order to obtain this final product. Otherwise you will get a salt, not a salt, like ionic compounds. So here you have CH3 CH2 CH. Now another H is being added by lithium aluminum hydride, and this carbonyl group is converted into hydroxyl group. Okay, and let's take ketones. Let's take like CH3CH2 C double bond or CH3. This is our ketone. Now when you add lithium aluminum hydride and water, okay, you will have the product like this. The hydrogen is being added, and here you have the OH2. Finally you have CH3 CH2 COOH, the carboxylic group, carboxylic compound. When you add lithium aluminum hydride for carboxylic with water, okay, you will obtain CH3 CH2 COH and 2 hydrogens. Here the important thing about this carboxylic acids reduction is, okay, this both hydrogens are from lithium aluminum hydride. Okay, these both hydrogens are from lithium aluminum hydride. Just like if you remember, we have talked the Grignard reagents reactions and its mechanism in our previous videos. So if you remember the carboxylic acids reaction with Grignard, the similar mechanism happens here too. So let's move on to the mechanism. Let's first take into the aldehydes. Okay, here you have, let's take CH3 CH2 oxygen and hydrogen. First, when you add lithium aluminum hydride, okay, here you have the lithium aluminum hydride. You know this lithium is a positive cation and this LiAlH4 is a negative part. So when we are, let me like draw it a little bit expanded version. So aluminum is there, so here you have the hydrogens and another 3 hydrogens. So this bond is relatively weak. What happens is this hydrogen bond, okay, this hydrogen bond is going to attack this carbon. Okay, this hydrogen is going to attack this carbon as H minus. That's what happens in the lithium aluminum hydride. So let's move on. Due to this attack, this bond will be broken, so you will have the product like CH3 CH2C H, and now you have a hydrogen here. It's bonded to carbon. Now you can put like lithium plus. There is the lithium plus here, so you can put the lithium plus on this place. Okay, you can put the lithium plus on this case, and that ALH3 is there. Okay, this is a neutral compound. If you remember, ALH3, it's a neutral compound. So when ALH4 is there like this, it's a negatively charged compound. So here we have the product, and now when you add water or H plus water, you can add a proton to this particular position. So you will obtain CH3CH2 OH, hydrogen and hydrogen. So in this case aldehyde, this is the only hydrogen which has come from the aluminum hydride. Okay, this hydrogen was there at initial, you can see. So when we are talking about the ketones, yeah, ketones, the same mechanism, right? nothing different. The same mechanism happens with the ketones too, but there's a little bit difference with the carboxylic acids. If we go through the carboxylic acids, so let's take a carboxylic acid like this, CH2, C and OH. So the same thing first happens. So let me draw the H3 and hydrogen. This hydrogen is attacking for this particular place, so this one is broken. We have our CH3, CH2, C. Oxygen is negatively charged now. We have a hydrogen here, we have OH here. Now you can put lithium plus here. Now you know that this particular compound is relatively unstable. Okay, this is relatively unstable. You can form the pi bond back again, but in order to do that, you need to remove this OH2. So you can draw this as this simple step, or otherwise you can, if you want more accuracy or if you want more more correctly, you can, like, before you removing this OH minus group, you can add a proton to it and make it a water molecule. So you know, like, OH minus is not that much a good leaving group rather than H2O. H2O is much better leaving group. So you can put water here. Okay, you can put water here, and there is a double bond here, and you can draw the attacking of this oxygen atom towards the proton. Now you have this. Plus, and here you have the hydrogen. So now you can remove this OH2 molecule with the formation of the pi bond. So you will have the final product like this: CH3, CH2, C and carbonyl group here, and also you have hydrogen here. This is our so we have obtained an aldehyde group, and then in the final step, again, you know, there are aluminum hydrides. So again, attack happens. Same thing happens, just like in the same, like this mechanism. Okay, with water you can obtain CH3, CH2, C, OH and 2 hydrogens. But the important thing, as I have told you, both of these hydrogens are coming from these aluminum hydrides. That's the difference between the aldehyde ketone mechanism and the carboxylic mechanism. So that this step is basically the same thing which I have driven here. So this is the full mechanism. In this step, I need to focus, like, this is the correct, right? This is the more accurate one, like, but you may remove the OH minus at initial, like you may forgetting about this protonation step. It's completely fine, but it may depend on your institution, right? If your professor's not like professor's notice about the addition of proton and make it a water molecule before it's leaving, then it should be there. So some professors are expecting this, some are don't mind it. So take a note about it. Not a big deal. I hope you are okay with it. So next video we will talk more about the organic chemistry.